In this video, we're going to begin by completing a chart. Okay, in this first column, these are the numbers written in their exponential form. And you'll notice that we go from 2 to the fourth all the way down to 2 to the negative fourth. So we're going to start to include some negative exponents here today. In the second column, we're going to expand what our exponential form looks like, and then we're going to give the evaluated form in our final column. All right, so let's go ahead and start with 2 to the fourth power. All right, expanded, that means I need 4 copies of the number 2 that I'm going to multiply. So I'm going to have 2 times 2 times 2 times 2. And evaluated, that's going to give me an answer of 16. All right, with 2 to the third, I need 3 copies of the number 2. 2 times 2 times 2, which is equal to 8. 2 squared, 2 times 2 is going to give me 4. 2 to the first power is just 1 copy of the number 2, so it equals 2. And as we've seen prior, 2 to the 0 power, 0 copies of the number of the base 2. I can't really expand that, but I'm going to look for some patterns that are going to help me evaluate this. So we noticed before that if I decrease the exponent by 1 in this column, my previous answer in my evaluated column gets divided by 2 in this case because that is our base. So 16 divided by 2 gets me to 8. And then I decrease the exponent again. So I do 8 divided by 2, and that gets me to 4. And then I decrease the exponent again by 1. 4 divided by 2 gets me to 2. So if I decrease the exponent again from the first power to the 0 power, I'm going to continue this pattern going on over here. So I'm going to take 2 and divide it by 2, which means 2 to the 0 power must be equal to 1. All right. Well, this is where we stopped previously, but now we're going to continue on to our negative exponents. So I'm going to go from 2 to the 0 power to 2 to the negative first power. I once again have decreased my exponent by 1, which means I'm going to take my previous answer and I'm going to continue this pattern of dividing by 2. So 1 divided by 2 means that 2 to the negative first power must be 1/2. And then if I decrease the exponent by 1 again from the negative first power to the negative second power, I'm again going to continue this pattern. 1/2 divided by 2, well, half of a half, that means 2 to the negative second power is going to have to be 1/4. And then I'll decrease the exponent again. Now I'm at 2 to the negative third power. So I'm going to, again, take my previous answer and divide it by 2. Half of 1/4, that's going to get me to 1/8. And then if I go and look at 2 to the negative fourth power, again, I'm going to take my previous answer. I'm going to divide it by 2. 1/8 divided by 2 is going to get me to 1/16. Okay, so hopefully you notice something in this evaluated column. We started at 2 to the fourth was 16, 2 cubed was 8, 2 squared was 4, 2 to the first was 2, 2 to the 0 was 1. Then 2 to the negative first was a half, 2 to the negative second was 1/4, 2 to the negative third was 1/8, and 2 to the negative fourth was 1/16. Notice that we have reciprocals. 2 to the fourth was 16, 2 to the negative fourth was 1/16. 2 cubed was 8, 2 to the negative third was 1/8, all right, and so on. So when we get into the negative exponents here, all we're really doing is taking the reciprocal of our positive exponents. So 2 to the negative first power is really just 1 over 2 to the first power. 2 to the negative second is really just 1 over 2 to the second power. 2 squared there is 4, so that's 1/4. 2 to the negative third power is 1 over 2 to the third power, and 2 to the third power was 8, so that becomes 1/8. 2 to the negative fourth power, 1 over 2 to the fourth power, which gets me to 1/16. Okay, so when we have these negative exponents here, we're really going to get into the idea of taking the reciprocal. All right, 2 to the negative first is the reciprocal of 2 to the first. 2 to the negative second is the reciprocal of 2 to the second, and so on. So in our next example, we're really going to focus on our negative exponents. All right, consider the expression 3 to the third power divided by 3 to the fifth power. How can we rewrite this as the base of 3 with a single positive exponent? Okay, and we say single positive exponent because we know the rule for dividing numbers that have the same base. We keep that base and we subtract the exponent. So 3 to the third divided by 3 to the fifth, since the base is the same, all right, let me get that out of there. Since the base is the same, I'm going to keep that base of 3, and then I'm going to subtract the exponents. Well, 3 minus 5 is negative 2, so that gets me 3 to the negative second power. All right, but I want my exponent to be positive. I don't want it to be a negative exponent. So what we're going to do, similar to an example that we did previously, we're going to rewrite this expression in expanded form. So we have 3 to the third power divided by 3 to the fifth power. That means in the numerator, I'm going to have 3 times 3 times 3. And in the denominator, I'm going to have 3 times 3 times 3 times 3 times 3. Okay, so there's what our expression looks like in expanded form. Now we're going to simplify as many common factors of 3 from the numerator and denominator as we can. Remember that any number divided by itself is equal to 1. So 3 divided by 3 is 1. 3 divided by 3 is 1. 3 divided by 3 is 1. All right. Well, we've simplified all the 3's from the numerator. We can't do any more simplifying. That means that the numerator then must be equal to 1. 1 times 1 times 1 is 1. So I'm going to have a 1 there. All right, but we still have 3's in the denominator. So now the denominator we're going to rewrite as a base of 3 with a single positive exponent. All right, we still have 3 times 3 in the denominator, which can be written as 3 to the second power. All right, so 3 to the third divided by 3 to the fifth is equal to 1 over 3 squared. And it also equals 3 to the negative second power, which we saw up here. Okay, so this helps to prove that 3 to the negative second power is the same as 1 over 3 to the second power. All right, 3 to the negative second power is the same as the reciprocal of 3 to the second power. So when you have a negative exponent, to create a positive exponent, all you're going to do is take the reciprocal and make that exponent positive. All right, so now that we have a good understanding of negative exponents, it's important to always rewrite your negative exponent as a positive exponent. In math, there's a concept that you're going to learn about in the future called scientific notation. All right, with the exception of scientific notation, negative exponents should never be left in your answer. We will take the reciprocal so that the exponent is positive. All right, and so this gets us to exponent property number 4. If an exponent is negative, take the reciprocal so that the exponent will be positive. X to the negative a power is equal to 1 over x to the positive a power. All right, and so that's what we're going to practice underneath. Okay, we are going to rewrite each expression using a single positive exponent. All right, so again, when we have a negative exponent, all we're going to do is take the reciprocal in order to make it a positive exponent. So let's take a look at example A. All right, here we have 4 to the negative third power. I want to rewrite it using a single positive exponent. So all I'm going to do is take the reciprocal. 4 to the negative third power is equal to 1 over 4 to the third power. My exponent is now positive. All right. Then we're going to evaluate any numerical bases. So I'm going to actually tell what the answer to this is. Okay, so my numerator, 1, isn't going to change at all right? But 4 to the third power is equal to 64. So 4 to the negative third power is equal to 1/64th. And again, that comes from 1 over 4 to the third power. 10 to the negative fifth power. Let's take the reciprocal first. That's going to equal 1 over 10 to the fifth power. And now that my base is numerical, I can evaluate that. This is going to be 1 over, well, I'm going to have 5 zeros after my 1 there. This is going to be 1/100,000th. 10 to the negative fifth power is equal to 1 100,000th, and that's the reciprocal of 10 to the fifth power, which is 100,000. Letter C, h to the negative 13th power, that's going to be equal to 1 over h to the 13th power. And I can't evaluate that because h is a variable, so that's how we're going to leave our answer, 1 over h to the 13th power. Notice in this example, 10 squared to the negative third power, I have a power being raised to a power. So I'm first going to apply that rule. When I have a power being raised to a power, I'm going to keep the base, which is 10, and then I'm going to multiply the exponents together. 2 times negative 3 is negative 6. So now I have 10 to the negative sixth power, but again, I need to have a positive exponent. So here I'm going to take the reciprocal. 10 to the negative sixth power is the same as 1 over 10 to the sixth power. And now I can go ahead and evaluate that numerical base. That's going to be 1 over 1 million. Okay, so this original expression is the same as 10 to the negative sixth power, which becomes 1 over 10 to the sixth power when we do the reciprocal, and that becomes 1/1,000,000th. In this last section, we have a few trickier examples, and our directions again are to rewrite each expression using only positive exponents. All right, so you'll notice in letter A, we have 1 over 2 to the negative fourth power. All right, my negative exponent is in the denominator of my fraction. We need to rewrite this using only positive exponents. So let's see what happens here, okay? So my numerator is 1, and when I have a negative exponent, I'm supposed to take the reciprocal. So 2 to the negative fourth is the same as 1 over 2 to the fourth power. And so now what I've got actually is a complex fraction. Okay, I have a fraction within a fraction. 1 divided by 1 over 2 to the fourth power. Well, I can't leave my answer like that. So if you remember, a fraction, all right, represents a division problem. So this means I'm going to take the number 1 and I'm going to divide it by 1 over 2 to the fourth power, okay? But when you divide fractions, you're really going to end up multiplying by the reciprocal, okay? So when I have 1 divided by 1 over 2 to the fourth, I'm really going to do 1 times, and the reciprocal of 1 over 2 to the fourth is just 2 to the fourth power. So 1 times 2 to the fourth power, my answer then is just 2 to the fourth power. 1 over 2 to the negative fourth power is the same as 2 to the fourth power, which is the same as 2 to the fourth power over 1. Okay, so when you're taking the reciprocal here, all right, if you'll notice, back in these examples, 4 to the negative third is the same as 4 to the negative third over 1. That became 1 over 4 to the third. Okay, my negative exponent went into the denominator. Well, down here, my negative exponent was in the denominator. 1 over 2 to the negative fourth became 2 to the fourth, which is the same as 2 to the fourth over 1. So my negative exponent then from the denominator went into the numerator. That's the idea here, okay? When you have negative exponents and you take the reciprocal, the exponent is going to end up in the opposite place, all right? So if it starts in the denominator, it's going to move into the numerator and become positive. If it starts in the numerator, it's going to move into the denominator and become positive. So looking at example B, all right, 1 over 8 to the negative seventh power is just going to be 8 to the seventh power, okay? And again, you can think of that as 8 to the seventh over 1. It was in the denominator being negative. It's going to move into the numerator and become positive. So 8 to the seventh power. All right, 3 divided by x to the negative fifth power. All right, so similarly, all right, this is going to be 3 over 1 over x to the fifth power. All right, but when we evaluate this complex fraction, 3 divided by 1 over x to the fifth is the same as 3 times x to the fifth power. And you really can't do much with that, so our answer here is going to be 3x to the fifth power. So again, our negative exponent is going to move from the denominator into the numerator. So this is going to be 3 times x to the fifth, and it's going to become positive. And again, you can think of that as being over 1. X to the negative third divided by y to the negative eighth. Two negative exponents, all right? When we take the reciprocal, we're going to reverse where these are located. So x to the negative third is going to move to the denominator and become positive. Y to the negative eighth is going to move to the numerator and become positive. So this is just going to be equal to y to the eighth power over x cubed. And again, we can prove that. X to the negative third is 1 over x to the third, over y to the negative eighth is 1 over y to the eighth. So when we evaluate this complex fraction, 1 over x to the third divided by 1 over y to the eighth, I'll now multiply by the reciprocal. So I'm going to have 1 over x cubed times y to the eighth over 1. And then 1 times y to the eighth is y to the eighth. X cubed times 1 is x cubed. And that again agrees with what we have there. So again, when you're taking the reciprocal, all right, your negative exponent is going to move either from the numerator to the denominator or vice versa and become positive. So again, negative exponents, think reciprocal.